In this screencast, I'm going to explain to you how to create or calculate a confidence interval on the mean when the variance is known. So this is a variance known case. See the previous screencasts if you don't understand the difference between variance known and variance unknown. Let's start out by assuming we are sampling a random variable with normal distribution, mean, mu, and variance sigma squared. These are the actual population parameters. We take n samples and compute the sample average, that's x bar, and you guys know how we would determine the mean and variance of the sampling distribution. So what are the mean and variance of the sampling distribution? That's right, x bar belongs to a normal distribution, the sampling distribution, with mean mu and variance sigma squared over n. Let's take a look at an example. Let's consider a population that has a mean of 40, a variance of 0.0625, meaning the standard deviation is 0.25, and we're going to take samples of size 10. This plot shows the sampling distribution, x bar, when we take a sample of 10 items. It's going to be centered about 40. And you might be wondering, if the standard deviation is 0.25, and we know that 68% of the distribution lies within plus or minus 1 standard deviation, why is this distribution so narrow? Well, remember that the variance of the sampling distribution is sigma squared over n, or the effective standard deviation is sigma over root n, and that's why this is much narrower. Remember, this is the sampling distribution. For confidence intervals, we want to find limits, lower and upper limits, such that we'll be 95% confident that the average of n items will lie between those two limits. If we're talking about a 95% confidence interval, that means we have something known as alpha, a risk level, is equal to 0.05. 95% confident means that we are 5% unconfident, in other words, and we have a risk level of 0.05. So keep this in mind as we go through the next couple of slides. We're trying to find these lower and upper limits, L1 and L2, such that 95% of the population lies between them. If we take our alpha, our risk level of 0.05, and we subdivide it into the two tails, each tail will contain alpha over 2% of the population. So again, our goal is to find numerical values for L1 and L2. If we take a look at L1, we can write the probability that x bar, remember this is a sampling distribution, is less than L1 is alpha divided by 2. We're looking at a 95% confidence interval, so alpha of 0.05, and that means the probability that x bar is less than L1 is 0.025. We can convert this to a z-value by standardizing. This means that z is equal to negative 1.960, and if we want to calculate what L1 is, we can back calculate out what L1 has to be, and we end up with L1 is 39.845 for the lower bound of a 95% confidence interval. We can also use the norm.inv function easily in Excel to calculate this number. We can do the same type of thing for the upper limit, L2. The probability that x bar is less than L2 is 0.975. Remember, the upper tail contains alpha divided by 2. And if we go through the math, we can calculate what L2 has to be. L2 is 40.155. So 39.845 to 40.155 contains 95% of the population of the distribution, and therefore we are 95% confident that the average of 10 items from this population will lie between those two values. We need to quickly discuss some important notation for today. Z sub alpha is the z-value that corresponds to having alpha probability to the right of it. We're no longer considering cumulative from the left. Z alpha divided by 2 would be the z-value corresponding to having alpha divided by 2 probability to the right of it. Because of symmetry, z alpha divided by 2 is also equal to negative z of 1 minus alpha over 2, shown in this diagram. We can conclude that z of 0.025 is 1.960, and z of 0.975 would be equal to negative 1.960 because of this rule up here. So this is some important terminology. It's not just important for the z distribution, it's also going to be important for the t distribution, the chi-square distribution, the f distribution, and others. Going back to our general derivation of L1 and L2, in general, we can take mu minus z alpha divided by 2 times sigma over root n, and this is because of our symmetry rule. Z of 1 minus alpha over 2 is equal to negative z alpha over 2. Similarly, L2 is equal to mu plus the same amount, z alpha over 2 times sigma over root n. And therefore, the probability that x bar is between L1 and L2, that's equal to 1 minus alpha, but we can substitute in L1 and L2 up here down into this expression, and this becomes our 95% confidence interval. In other words, if we knew the true population mean, and we either knew or could get a good estimate of the population standard deviation, we could be 95% sure that a random sample of 10 items will have an x bar, a sample average between these two limits. In other words, 95% of x bar will fall in this range, will fall between 39.845 and 40.155, assuming that the population mean is 40. We would be 95% confident that the next value of x bar when n equals 10, or any future value, again, when n equals 10, will fall in this interval that is centered about the true mean of 40. 40 is right in the middle of this 95% confidence interval. It turns out that calculating confidence intervals on x bar is not as common. Instead, what we do is we want to rearrange this and look at this in a different way such that we can have confidence intervals on the mean, the true population mean. Because remember, oftentimes we don't know the true mean and we want to estimate it from our sample statistics. So let's turn this argument on its head. If we know sigma, but we don't necessarily know mu, but we have our sample average, x bar. Here, let's just say we have an x bar of 39.90. We can shift the interval computed before. We're just translocating it left or right, but we're going to center it about the x bar value, the x bar that we get from our sample of 10. We can then claim with a 95% probability that the true mean, mu, the population mean, lies within this interval. So in other words, we're starting at our x bar, and we're going to go out the same distance, and that's going to be our 95% confidence interval on mu. We don't know mu, but we're estimating it here. This is known as a confidence interval on the mean. And we can say that we are 95% confident that the true mean lies between, in this case, 39.745 and 40.055. Also, because we're 95% confident, this means that we run a 1 in 20 risk of being wrong. Remember, an alpha of 0.05 is a 1 in 20 risk level. If we start with our two-sided confidence interval on x bar, shown here that we derived earlier, and we mathematically do some manipulations, we subtract mu from each term, subtract x bar, multiply through by -1, which reverses the less than signs, and we rearrange, we get that the confidence interval on mu now, instead of x bar, the confidence interval has the same width. There's a 95% probability that the true mean lies between x bar minus z alpha over 2 times sigma divided by root n and positive z alpha over 2 times sigma over root n. Another way of looking at this is shown here. If we don't know mu, 19 out of 20 times, mu would be contained within that confidence interval. So these are 20 different samples. Only one of these out of the 20 contains a mean that's not in our 95% confidence interval. So just keep that in mind. Occasionally, mu will not be within your confidence interval. Let's go through an example. Sulfur dioxide is a product of fossil fuel consumption. We can record some data here. N equals 10. We get an x bar of 53.92 and a sigma of 10.07. We're assuming that we know the variance, the population variance. Again, this is a variance known case. Maybe we've got a long record of data and we know that that standard deviation is pretty accurate. We can be 95% sure that the actual mean level lies between two limits, L1 and L2, and that's what we're trying to find. This is our 95% confidence interval. We can take our equation for the confidence interval on the mean, and we can plug in our sample statistics, X bar 53.92. We get a sample standard deviation of 10.07 that we're going to say is approximately equal to the population standard deviation. We can plug these numbers in, and we end up with a 95% confidence interval on the mean, 47.68 to 60.16. Thus, we can be 95% confident that the actual population mean lies between these two numbers. Sometimes we can create a one-sided confidence interval. This is actually seldom used, but you can set it up such that you're 95% confident that the mean lies above some value. It's a one-sided confidence interval. And the equation for that, the expression for this, is shown down here. Sometimes you'll want to estimate the number of samples required to get a certain error in your confidence interval. Rearranging these equations, x bar minus mu, we're going to call capital E, that's your error about your x bar. And if we solve for that, we can get n equals z alpha over 2 times sigma divided by your error that you desire, and you square that. This is useful in planning out experiments to obtain statistical significance in results. As an example, we need to be 90% certain that the confidence interval on the mean has a length of 5. So maybe that 5 is important. We estimate the population standard deviation to be 5. How many samples do we need to take? E is going to be 2.5. That's our total interval divided by 2, because E is only on one side of our x bar. Z alpha over 2 here, this is a 90% confidence interval. Alpha equals 0.1. Z of 0.05 is 1.645. We multiply that by the standard deviation, divide by E of 2.5, and we square that. We need 11 samples in order for our 90% confidence interval to have a length of 5. Hopefully this screencast gave you a good introduction to confidence intervals on the mean when we know the variance.